Standard form of our quadratic is right here in our little like goal. It's in the form ax squared plus bx plus c is called the standard form of a quadratic equation. And I threw a nice little cutout of kind of the parent function of what's called of the quadratic. It's the function f of x or y equals x squared is our parent function. Okay, and it looks like your favorite old parabola, that kind of U-shaped function. And there's a couple important features of our parabola. In particular, there's the vertex of our parabola, which is the lower or uppermost point. The lower or uppermost point. Does anyone remember from Algebra 1 if I give you standard form how to calculate where the vertex is? I remember this from way back when. It was a formula. It involved the coefficients. That probably didn't help things. That's awesome. The x value, hopefully from Algebra 1 this might jog great memories. The x value of the vertex in standard form is minus b over 2a. That might have jogged some memory. If not, that meant you were sleeping during Algebra 1. The x value of the vertex is negative b over 2a, or opposite of b over 2a. And since the vertex is a point, then if we know the x value, how are you going to find the y value? Y equals plug in x to equation. The axis of symmetry is kind of the other nifty feature of a quadratic. In the parent function, the axis of symmetry is the line the line x equals 0. It's the line that divides our parabola into two equal parts, two very symmetrical parts, hence axis of symmetry. Every point is mirrored on either side of this axis of symmetry. And what's awesome is that the axis of symmetry is pretty easy to find if you know what the vertex is. Because if you want to find the axis of symmetry, it's the, probably start writing with the dotted line. Is the line, not a bad day today, x equals the x coordinate of the vertex. So for example, if I throw you this little graph here, we could do a quick sketch of this and do a comparison. In particular, since we have a parent function, if you recall from last chapter, was it last chapter or the chapter before, we asked you to compare functions to its new functions to its parent, like slide, shifts, stretches, reflections, that sort of thing. The same thing can be applied to parabolas. In particular, if we're multiplying to the x squared, what kind of transformation is this going to go under? Is it going to be a, Louis, what are we going to do?
It's going to be a stretch or shrink.
Like a stretch or a shrink, yep. And if it's a multiplied by a number less than 1, it's going to be a stretch it out or a shrink? Shrink it. So we're going to shrink every y coordinate by 1/2 from the original parent function. So if the parent function, I'll draw in blue, the parent function is drawn in blue here, then our new function, our function, should be half as tall everywhere for every x coordinate. So our function starts at 0, 0. Then if we go over 1, we're going to go half as much as we did before. So instead of going up 1, we'll go up half of 1. And if in the second time we went over 2, up 4, we'll go over 2 and up half as much. So we'll go over 2, up 2. And so on. And if you have half of this parabola, and we have this, we know its axis symmetry goes on the middle, then you could just mirror every point and get yourself a parabola that's relatively quickly drawn. This being y equals half of x squared. Right. The comparison would be, well, how do we do this? Well, we said it's a vertical shrink. It said shrunk by a half, so we'll shrink it down by a half. You did not need to draw that original graph, the blue one, but when we're starting out, it's not a bad idea to have a visual of how it's changing, and so forth. I know that this is some things that I've done to the original function. I've multiplied it by a negative number, so there's a reflection. I've multiplied it by 2, so it's being stretched out by 2. Should be stretched by a factor of 2. So I'm multiplying the x squared by 2. I'm also adding 4 to everything. So thinking back to our comparisons of parent functions, when we add to the function, that's a vertical, like sliding up and down. That's an up and down slide. So we're going to slide this up by 4 by using comparing to the parent function. So I'm going to slide this. So my new graph should look like it's the old one, the original, slid up 4, slid up 4. It's upside down. It's been reflected. And it's stretched out by a factor of 2. So the old one went what? Over a 1, up 1. So my next one is going to go over 1.
Down 2.
And it's stretched by 2, but reflected. So over 1, down 2. My original one went over 2, up 4. So I'll go over 2 and down 8. 8. It's a parabola, so it's got a nice axis of symmetry. So what that tells me is that anything I do, really, not necessary. Anything I do to one side, I can do to the other. So anything I do to one side of this line, I can do the other. So I can mirror this point. I'm 2 over, I go 2 over, 1 over, 1 over, my original. And now I can get my parabola is upside down. If I give you an equation in standard form, and you know it's in standard form because I have x squared and I have a linear x, so it's not grouped now nice and neatly as something squared plus something else. Now I've got an x squared, I've got a linear term or something else. In order to graph this, you could either use your graph calculator to make a table of values. That's actually less efficient though than using these facts about a parabola. In particular, if you find, I use that word a lot, don't I? Vertex and the axis symmetry. If you find each of those two things and plot them on your graph, then we can actually graph these very quickly. In particular, man, I gotta stop that. How do we find the vertex?
Negative b over 2a.
It's on the front side, right? So the vertex, the coordinate of our vertex is negative b over 2a. Or opposite of 6.
Just keep this with the box.
Oh.
It's important.
Thanks.
Hey, is that your new frog stick box?
Well, that's what it came in, yeah. I got the stick.
Alright, I'll switch to that later.
Opposite of 6 over 2 times a. A is the coefficient here, which is what, -1, is our x coordinate. So that gives us what? Positive 3. Opposite of b over twice of the a coordinate. So our x value of the vertex is at what? Is at -3? Positive 3? Positive 3. -9 plus 18 minus 8 is 1. So the vertex is at the point 3, 1. 3, 1 is our vertex. Where's the axis of symmetry? Right through the vertex. So the axis of symmetry is the line x equals 3. So now all we need is some y values on the either side of this line, and we can just mirror them over. The easiest y value to find is the y-intercept. How do you find the y-intercept? How do you find the y-intercept of any equation? You did it in the warm-up.
Plug 0 in for x.
Plug 0 in for x. So what's going to be left if you plug 0 in for x in this equation? -8. So the y-intercept is at y equals -8. 1, 2, 3, 4, 5, 6, 7, -8. What's nice about this point? You get another point for free if you know any point on either side of this line. How am I going to get another point for free by knowing this one? Yeah, use the axis of symmetry to mirror this thing over. So if here's axis of symmetry, then I should have this point should be over here as well. And if you really want to, you could find a couple points in between. Or if you're really lazy, you could sketch this parabola through those points. Y value of the vertex. And just by looking at the equation without plugging any numbers in whatsoever, how in the heck are you going to find if it's going to be a max or if it's going to be a minimum? How would you know that? Just by looking at the equation. You can identify one thing in the equation, it'll tell you whether it will be a max or a min. Joey?
If there's a negative, if there's going to be a maximum, if there's no negative, then it's a minimum.
Absolutely. If there's a positive, if it's a positive value, then the graph has got to look something like this. It's got to look like a right side up parabola. So the vertex, therefore, is the lowest point. If it's a negative value, that means it's an upside down parabola. So the graph, somehow, some way, it's got to look like this. Which means the vertex is up here. Which means we have to have a maximum. What that number is, you'll get by finding the vertex and finding the y value of it. But you know that it has to be a biggest number. It has to be a maximum if the leading coefficient's negative. And it's got to be a minimum if the leading coefficient's positive. Because a positive leading coefficient gives you a right side up parabola. And a negative leading coefficient flips it upside down. So it gives you an upside down parabola, or a negative leading coefficient gives you a kind of a maximum. And to find that, find the vertex and tell me what the y coordinate